It's a big pleasure to have Vasilis Kemerlis here. Vasilis is an associate professor at Brown with tenure. We've known each other for a bit more than a decade and a half or so.
For a decade, we just tried to arrange this.
For half a decade, we tried to arrange this. Very happy that we finally could pull it off. Absolutely. Vasilis is well known for his systems and security research, and therefore an excellent fit for the security seminar series here. Very excited. That's what I said. What did I say?
It's a security center.
Oh, yeah. Well,
That's a different center.
that's my single track mind. System seminar. So yeah, Vasilis, take it away.
Right?
Please just turn your camera on. Sorry.
On or off?
On.
On.
Is it okay if we ask questions in the middle, or should we wait?
There you got it.
Okay, but I'm going to be moving around. I'm not sure how,
It has the whole front of the room.
Okay, cool.
Thank you.
All right, so yeah, thank you very much for the great introduction, and thank you all for being here today in the systems seminar. So today I'm going to be talking about building trustworthy, let's say, operating systems. So basically, this is a kind of summary of pretty much what we have been doing in my lab for the last 4 or so years. Feel free to stop me, ask questions, whatever. Mandatory advertisement slide. So I work on various areas in systems / security, thermal protection, software hardening, fast testing, side channels, hardware security, all sorts of things. Today, I'm going to be primarily focusing on our work on protecting operating system kernels, which is an area that I really like. This is also the area that I did my thesis on. I'm going to be primarily focusing on 4 projects called XMP, SafeSLAB, EPF, and BeeBox. We're going to see what these are about. If anyone is interested about all the rest here, I'm happy to chat afterwards, offline, or whatever. I'm also going to be taking this as an opportunity to also talk a little bit about the history of this field, how it has evolved, how kernel exploitation worked in the past, and kind of motivate a little bit the stuff that you're going to hear today. So let me start with basically the operating system kernel. For those who are not very familiar with what the thing is, it's basically the heart of an operating system. It's that piece of software that sits basically between the hardware and the applications. And it does 2 things. It abstracts the hardware to the apps. So apps don't really know about what the CPU is, what memory is. They know about abstractions of these things. They know about execution threads, virtual memory, and so on and so forth. And the other thing that it does is that it manages resources. And it does that for 2 reasons, for performance, but more importantly, and what is relevant for this talk here, for protection. So all these nice things that we have today in our systems, such as isolation in terms of virtual memory, the fact that every application cannot step into freely what another app is doing, confinement in things like namespaces or access control. Say you have a file and you want to say this app can write here, this other app can only read from here. The thing that basically does all these things is the operating system kernel, that piece of software that provides the isolation, provides confinement, and implements access control policies. So it's very important in terms of, if you think about it in terms of significance in the software stack, it's very important for that level here to kind of operate properly or in a trustworthy manner, because the security of the system can only be as good as that layer only. And so in other words, if that thing goes down, you cannot really do much. Now, speaking about the kind of the state of things with respect to vulnerabilities, given what I've said, you would expect that this piece of software is going to be something which is small, it's secure. We kind of pay attention to what kind of code we put there because it's very critical to the operation of the whole software stack and so on and so forth. But the reality is completely different. The operating system kernel in general for pretty much every commodity OS is super bloated these days, which also leads into a ton of different vulnerabilities. What we have here, what I show here is basically the number of vulnerabilities in the Linux kernel, tracking it from 1997 up to 2022. The last 6 years in this graph, we have more kernel vulnerabilities than the previous 20 years combined. There's various reasons for this, which we can discuss if you're interested. But the point is that all these things here, you should think of them as an opportunity for the attacker to compromise completely the system. And go around pretty much every security mechanism. Now, the average bug fix time for all of these things here is basically 60 to 66 days, roughly 2 months. So for each and every bug there, it takes roughly 2 months to fix it. Some of them, they've been open for 230 plus days. At the same time, the average time for the bad guy, let's say, to develop an exploit is just 2 days. So if they know for a particular vulnerability, if they find a vulnerability, they can actually produce a working exploit in 2 days. Yes.
Just to be fair, not all the bugs are exploitable or
Definitely.
problematic.
Yeah, and not all of the bugs provide the same capabilities to the attacker. Most of these things here, though, the ones that I have plotted, because I only care, well, as we will see later on, I mostly care for memory errors, like vulnerabilities that basically can leak into corrupting memory. All these things here, they can at least crash the system. Okay, so I'm not tracking here things such as logical errors, let's say, that can lead into authentication bypass or stuff like that.
But even then, there's a wide gap between crashing a system and exploiting the memory block.
Huge gap. But a lot of them are exploitable. We see, as we'll see later on. Now, speaking about what kind of vulnerabilities are these, the vast majority or the ones that I'm interested in tracking here are memory errors. So if you have ever heard about things such as a stack or a heap overflow, a use after free, pointer arithmetic errors, things like that, all these are examples of what we call memory errors. These are primarily vulnerabilities that you can find in languages such as C, C++, and handwritten assembly. If you're not very familiar with that, there's just like, all these things basically can be, can fall under two different categories: spatial memory safety or unsafety, depends on how you see it, issues. Cases like these are basically situations, let's say that we have a pointer pointing into an object. There is a logic in the code, such as pointer arithmetic errors, overflows, and things like that, that can lead into writing into a different object following the legit object, the legit referee for that particular pointer. And that thing can be an object which is really adjacent to the one here, like object one here, or something else. Like, so you can have contiguous, basically memory corruption, or memory disclosure, non-contiguous, you have all sorts of things. So spatial memory safety violations, you can keep in mind that, like the model is that you have a pointer, you can go out of bounds, and you can corrupt or leak stuff relative to the legit object. The other class, or basically type of errors that a couple of these things fall under is temporal memory safety violations. So in temporal memory safety violations, what we have there is something like a pointer pointing into an object. You dynamically, let's say you do malloc, you have your object and you're pointing there, then you free that area. So that thing gets freed now, but the pointer 0 becomes a dangling pointer and still points in this location. If you end up doing another allocation that is going to reuse completely the same slot or something else close by, let's say you allocate another object, that thing gets pointed by pointer 1, but you can still write in this first area here through pointer 0. You can still either leak or corrupt the full object 1 or part of it. It again leads into this problem of being able to corrupt things in memory or leak things from memory. So basically, these are the like the model for pretty much all these kinds of types of memory errors here. Now, Sun kind of classified this as one of the top 25 most dangerous software errors. A lot of vulnerabilities reported by Microsoft and Google fall under this category. Surprisingly, both of them say 70% of the CVEs are unique numbers that basically track vulnerabilities are assigned to memory safety problems. Go ahead.
It's a random question. Top 25 seems weird, right? It could be the 25th most important thing, meaning that there are 24 things that are more important to take care of. So where on the 25 list?
So that's a good question. Actually, you know what? They also I think they also released a new list like literally yesterday or I don't know 2 days ago. So basically, I think the way it sounds basically is by seeing it has categories, CWs, and sees how many CVEs touch that CW. And then it does a rank. Okay, so it says, okay, out of all the stuff we saw today, this year, or these past years, like arbitrary rights, buffer overflows, fall in the top, whatever. I think that's how they try. Now the oath is for the National Cyber Director because apparently, yes.
Sorry, just a question a few slides ago when you showed the vulnerabilities across the years. Is there a reason why 2017 had the spike it did?
Great question. Yes. So around that time here, specifically in Linux, they started doing fuzzing, like fuzzing the operating system in a scale much, like much bigger scale than that. So syscaller and sysbot basically were put into work, and a lot of these things here result from basically automated techniques to identify them. The majority of the stuff in the past were due to either someone manually trying to figure out what was going wrong, or identifying, let's say, I don't know, like a crash in the wild.
And so what you're saying is they just got discovered then, right?
Yep.
And do they track sort of when were they introduced? Are they sort of being introduced uniformly, or
there are studies who actually try to do triaging, like basically go back and figure out this vulnerability, this issue, like when was the code that actually introduced it and stuff like that. But here we track like when basically we track CVEs, which is the number that was assigned to the vulnerability when it was discovered plus some time afterwards. Does that make sense?
Yeah, thanks.
Any other question? All right, so as I was saying, apparently we also have a national cyber director, apparently.
Until next year.
So again?
Until next year.
Yes.
Is it virus?
Probably.
No, Department of Efficiency, right?
Yeah, we will see. We will see. Anyway, but now we have one of like a national cyber director as well. So last spring they released this statement, which is basically a report about raising awareness for memory safety issues, especially in software that is deployed in critical settings. It's an interesting report because they have the Department of Homeland Security basically tracking exploited vulnerabilities in the wild, and these guys report that 58% of the vulnerabilities exploited in the wild, they did involve memory errors, okay, as part of some step in the exploitation. So it's an important problem, I think. So let's now move on to kernel exploitation. So the way, like this field has evolved, it kind of mirrors a little bit how the exploitation of memory errors work in user space, but there are certain things which are kind of distinctive for the kernel setting. So I'm going to talk a little bit about that. At the same time, also cover a little bit of the history of that thing. So like early days, the technique, one of the primary techniques to exploit memory errors in kernel code was by using a technique called code injection. The idea there is that you interact with the kernels through some API, vulnerable API. You end up basically pushing data into the kernel, which is code. Literally, the bytes there correspond to code. Then go and trigger a vulnerability that is going to corrupt a code pointer. Think of a function pointer, a return address, basically a pointer that points into code, and then cause the kernel to dereference that pointer. And then if you do that, instead of actually, like going to invoke a legit function from the kernel code, you would end up executing code injected into the address space. That's where the term code injection comes from. This is not a problem these days because of things such as non-executable memory and kernel address space layout randomization. These are two standard defenses also deployed in pretty much every commodity OS in user space. So these kind of killed completely code injection, at least as a first step in the exploitation process. Now, a very popular technique right after that was something called an array-to-user attack. And in an array-to-user attack, the idea is that exactly the same. You kind of find vulnerabilities that you can trigger through buggy APIs. Instead of trying to inject code in kernel space and execute it from there, because as a user process, you control the user space part of the address space, you could place either your code or whatever data structure, let's say you want to dereference, fake data structure in user space. corrupt code or data pointers in kernel space and override those with user space addresses that then trigger the kernel to actually go in the reference. Yeah, this is where the term read to user kind of come from. So back in the day, I built one of the first software-only systems to defend against this. It's called Tegard. Nowadays, if you have heard about things such as SMEP and SMAP, if you come from the Intel world, or PXN and PAN, if you know ARM, these are hardware features that basically prevent when the CPU is running in, let's say, privilege mode to go like arbitrarily in user space and start either executing instructions like fetching instructions from this part of the address space or dereferencing stuff. So we have this kind of isolation assisted by hardware. Okay? There's also another interesting attack that was also part of my dissertation work that I came up with, which we call it read to dir. So most operating systems, what they do is that they take the whole physical memory and they pre-map it or map it in the kernel address space. And they do that for management purposes. Okay, that region is called FISMAP, for those who are aware of that. And the problem that this thing creates is that, let's say if you have a scenario like this and you have a data structure that you want to dereference and you override the data pointer with the user space address, and you have SMAP basically blocking you. If you have the whole RAM mapped inside the kernel space here, you can find an alias for that thing here. And then instead of basically doing this, you can find the address inside the alias region and dereference it from there. And the whole idea of a read-to-dir attack was, okay, how can we find this address? If we cannot deterministically find it, can we probabilistically exploit it, and yada, yada, yada. This is something that I published, I think 10 years ago, actually, 2014. And there's also a defense in that paper for the same attack. Unfortunately, the sad reality is that 10 years after that, with the exception of Windows, all operating systems are still vulnerable. There are some, like advancements, but literally the same attack works these days. Yes.
I just want to be clear. You're saying they map the entire physical memory into the kernel space?
Yes. So it depends on the architecture. So 64-bit architectures take the whole RAM and pre-map it there. 32-bit architectures do a portion of it.
Right. Why map the whole thing?
It helps them in terms of performance. So every time you want to do a translation from physical to virtual within the kernel, you can just do it with a base and offset kind of translation rather than going through translation. It also helps a little bit sometimes when you are in interrupt context and stuff like that, and you want to very quickly access something. You don't really have to do like an allocation that is going to result into dynamically, let's say, going and getting a page, mapping into the page table that would result into another interrupt.
So it's all for efficiency.
Primarily performance, yeah. Any other question? Now, again, let's assume that now this and this, they don't exist. As I said, the sad reality is that this thing is still vulnerable, or some systems are still vulnerable these days. On top of that, we have been, like all these years, there have been additional advancements so as to kind of prevent exploitation by things such as hardening how the kernel heap allocator works, and we're going to see our work that we have done in this area as well. Constifying data, so like if you have certain pointers that like they are prime targets for attacks, they go and basically make them read-only, immutable, and things like that. But primarily, like the kind of the exploitation as far as the kernel goes, kind of evolved from code injection to read to dir to a technique these days, which is called code reuse. So what we do today, instead of basically jumping to user space and stuff like that, is something which is, if you have heard the term return-oriented programming, that's just an instance of it. Basically, what you try to do is to reuse benign code to implement a malicious functionality. And the way to think about that is, think about, you have a function pointer, it points to the beginning of a function. If you can take that function pointer and put it in the middle or towards the end and you dereference it, you're going to execute a small snippet of code. And that small snippet of code can be something like, for instance, I don't know, pop a register with the contents of the stack and then a return instruction, stuff like that. By executing these small snippets of instruction from here and there, these are all benign instructions. You can basically perform arbitrary computations. This is Turing complete. Instances of this thing are again like return-oriented programming. There is other kinds of code reuse. jump-oriented programming, call-oriented programming, and a bunch of other things, depending on how exactly you stitch together these payloads. So here, in this kind of attack, the payload itself is just a sequence of addresses. So if I take this and inject it into the kernel, that's by the way, a real raw payload that many years ago I wrote for a 32-bit x86 Linux. That performs privilege escalation. So it tries to prepare a little bit the arguments to call to functions to elevate the privileges from a regular user to becoming. So the payload here basically looks like a sequence of addresses, and all these addresses correspond to small instruction snippets. So that's primarily how exploitation is performed these days. IBM did a study about memory error exploits in the wild. They found that 90% of them basically use some form of ROP. Which makes sense because of SMAP and the other hardening mechanisms that I said before. A lot of high-profile exploits lately, they also use this. Bleeding Tooth from Project Zero, the NetFilter exploit that was exploited in a while a couple of years ago, and so on and so forth. And primarily, there is two different kind of approaches to dealing with this. This is where we are, like, we're coming towards where we are right now. Okay, so in terms of research, there is an area which is called Likert resilient code randomization. In order to break this, one thing that you can do is that you can randomize the code in a very fine-grained manner. So let's say every time you compile the code, you permute where, like functions are going to end up in the image, instructions inside functions and things like that. Because in order to reuse something, you need to know where it is. You need to know the address of that. So by permuting the instructions, you basically break the assumption of the attacker knowing that in this address, I have this instruction sequence. And on top of that, you need to make it in a way that the attacker is not able to actually discover that, like read that somehow at runtime by exploiting a memory disclosure vulnerability that will allow them to read. So that's where the Likert resilient code randomization term comes from. In the setting of the kernel, we have basically worked in this area as well. We had a system called KRX publish a couple. So this cryptic name, readx or execute, that's what KRX comes from. And it's basically tries to imitate the writex or execute policy. Basically, it says that if something is executable, it shouldn't be readable. Anyway, I'm not going to get into the details of this. I'm happy to discuss afterwards. The other kind of path towards defending against that is something which is called control flow integrity. And we also have some work done there. If you're using latest versions of Linux, you have something called FineIBT, which is basically a hardware-assisted CFI approach. If you're interested to know how this works, we kind of help with the design of that. I'm happy to discuss later or check the paper on that. So let's go to the first system that I'm going to talk about. So with all these things like Likert resilient or CFI, let's assume that code reuse is not a problem. The kernel still has memory errors, like memory corruption vulnerability. So if we cannot reuse code if the attackers cannot reuse code, what are they going to do? They can still go and perform what is called like a data-only attack. And in a data-only attack, the goal is to corrupt memory. But instead of corrupting things such as function pointers or dispatch tables in order to hijack the control flow of the kernel, go and kind of corrupt security-critical data structures such as page tables or process credentials or tamper with cryptographic material and things like that can also help escalating the privilege inside like the system under attack. If they tamper with page tables, then they can kind of alter memory mappings. If you tamper with process credentials, you can bypass access control and authorization, and so on and so forth. So XMP is basically a system that we built that tries to provide intra-kernel space data isolation. So inside the address space of the kernel, what we want to do is that identify security-critical data structures, say page tables or process credentials, and make sure that despite the fact that the attacker still has the ability to corrupt things in memory, it's not going to be able to touch the pages that they contain, the page tables, credentials, whatever is the security critical data structure we want to protect. Yeah.
You're only interested in write protection, but read protection is just as important to microarchitectural attacks.
Yes, we care about both. I'm, like primarily, kind of explaining it using write. As you will see, the thing that I'm going to present basically allows you to do any kind of policy as far as read, write, and execute goes.
So can you really partition data this way? Because a lot of the data structures that are security critical, sometimes they sit on lists or trees or things that are all spread out and dynamically allocated all the time, right?
You have to, you're going to see how we do it, but basically it's a combination. The way we do it here is by using a combination of hardware. Like we are repurposing a hardware feature that is meant for virtualization for intra-kernel space isolation. But ultimately, you have to rework a little bit how certain allocations happen. So for instance, if you want to have page tables isolated, you need to make sure that they're going to land in pages that are not mixed with data which they shouldn't be isolated.
And that's hard. I mean, to think about the capabilities of in a task struct, right? Those are just part of the task struct, and God knows where the task struct is allocated.
And it's not only that; it's also the pointers to those things,
Yeah,
as you will
exactly.
see in a second. So the high level idea here is that we want to do intra-kernel space partitioning, and what we want to have, we're going to have this notion of a domain. A security domain is basically, think of it as the set of like memory pages which are accessible at this point from the kernel to. Think of it again as the pool of pages for credentials, page tables, whatever is the critical data. And we want to be able to have this ability to switch between domains. Why? Because for the most part, we want to run the kernel without access to the sensitive data. Okay. However, if the goal is to have no access at all, then we could easily just remove those data and get done with it. But in reality, the kernel needs to operate on those, right? So you need to update page tables. You need to read process credentials. You need to create process credentials, and so on and so forth. So there are legit, basically, code agents into the kernel that need to operate on those. And therefore, we need to have a way to kind of switch between protection domains, do the legit access to them, but then for the kind of, for the most part, let's say, of the kernel lifetime, they shouldn't be having access to them. So that's the whole idea behind XMP. Now, in order to understand how XMP works, we need to talk a little bit about a hardware feature which is called extended page tables. This is a hardware feature that is used a lot in memory virtualization for running VMs. And it's basically, like a form of nested paging, if you will, right? So the same way we have page tables that they translate virtual addresses to physical addresses, we have another layer of translation that goes from guest physical memory to truly host physical memory. And this is basically what you have in your systems when you run a VM. Okay? So that's how, this is the thing that basically allows two different VMs have their own, kind of physical pages isolated. Okay? Now, the interesting thing with this is that we can have many of alternative extended page tables, each of them doing their own translation, each one comes with their own permissions, and so on and so forth. In Intel, we can have up to 512 of them active at the same time, and we can very fast switch among them using, as we'll see later on, an instruction called vmfunc. Okay. So this is different from traditional paging that you do, you have to update CR3 to point to the next page table hierarchy. Here, you basically initialize all the 512 of them, and then at any point in time, you can select which one is active using one instruction. Okay. That's the kind of background. So the way, say again?
It's like graphics, triple buffer.
Yeah, well, it's an interesting, depending on where you come from, it's an interesting way to see it. So the way we use this in XMP is the following. For every, critical data structure that we want to protect, we create a whole set of new nested page tables, EPTs, that basically do what? They map, first of all, as far as the mapping goes from guest physical to host physical memory, we use something called an identity mapping. So guest physical, literally memory 0 is gonna map to host physical memory 0. So in other words, as far as the mapping translation goes, think of it as an op. Okay, it's there, but it's not. Okay, that's what the identity mapping is. Now we have a set of EPTs that they all map from 0 to 0, 1 to 1, 2 to 2, like in terms of pages. And we have a separate copy of those things for every critical data structure set we want to actually protect. think of page tables, credentials, yada, yada, yada. Okay? Now, the interesting thing here is that as far as translation goes, it's nothing, as I just said. So we haven't done anything yet. So the interesting thing is that we can have different permissions in every one of these things. So what we do is the following. Say we have, here we want to have access to page tables. All the pages that they contain page tables are going to be having the read and write permission. In all other domains, they're going to be mapped as no access. Or we may want to have a domain where page tables are read-only and writable, but read-only here. So as a primitive, we can have flexibility to assign any type of memory permissions we want. Now, if we have security critical data going to kind of domains, if we have n protection domains, we're going to have n plus 1 EPTs. We also have one, but we call it the restricted one, that basically accumulates the most restrictive setting across all the EPTs. So think about here, for instance, if you have read-write for this page and no access here, again for the same page, then no access is going to be propagated to the restricted one. When the kernel is executing, it's always executing with the restricted. So if you have a vulnerability and you want to corrupt page tables, credentials, or whatever, and you try to access that page that actually has it, you're going to get a fault from the EPT level. If you have a function now that legitimately needs to operate on that data, we're going to do a switch. How do we do the switch? We do domain switching using a function called vmfunc. That's 150 cycles basically, depending on which CPU you're running it, and we can do the switch here. The function is going to operate on the data. EPT will allow it, and then we go back to where we were before, or we can go to a different domain depending on what the code wants to do.
That one will validate the TLB likely, right?
So actually no.
Oh, you have address space IDs in there?
You have tags with the virtual process ID basically. So that's why it's very fast. Although that's not something that we do. We get it from the hardware.
How do you decide whether it's legitimate to go to one domain or
Great
another?
question. So this is manual. So we have to actually patch the code
Oh.
that says, or semi-automatic. So we can do that semi-automatically. So this is what I was getting at. So the transition can happen. This is the primitive that we have, right? So as a primitive, we can, if you want to have just one instruction being executed, you can be in restricted, switch a domain, just execute a single instruction and then come back. If you want to have whole functions being executed, that's up to you. How are we going to do that? You need to instrument the code with vmfuncs. So this either has to be done manually or semi-automatically by having a compiler pass that is going to track accesses, let's say, to specific data structures.
Which means if you have a vulnerability there, then you go back to square one.
Yes. So the points that operate, let's say, on that, they are kind of become trusted, if you will. Right? So in other words, if I have a function that basically updates a page table entry, I assume that it will be updating the page table entry correctly. So I'm not fixing bugs there. Although I'm protecting it from all the other pieces of code that may contain vulnerabilities, and they don't need to touch page tables.
So I want to understand one thing, right? So you are in ring 0, but to do vmfunc switch, right? You must be in EL-1, no?
No, you can even do it from user space.
You can do for
So vmfunc is not an instruction that basically taps.
not privileged. It's weird. Isn't it changing fundamentally how physical is translated to physical? How is that accessible?
You have to. So the way it works is that you first need to virtualize the CPU, and then once you do that and you bring that CPU into being, I don't know, ring -1, let's say, you allow vmfunc to run in.
Oh, I
that
see.
CPU.
So you deprivilege that instruction to run at a lower, the higher ring. So that means that basically at some point you switch to -1, set up all these descriptors. From that point on, you can only switch.
Because the vmfunc thing as a function, as an instruction, the only thing that you pass is you put in a register basically an index which is basically an index between 0 and 5. You don't really control at the EPT level the root pointers that they point to EPTs and stuff like that. These are all pre-mapped. So it's a primitive that it exposes basically to ring 0 to do the switching on demand, so as to allow you to do fast.
So that means its parameters are also vulnerable to a fault.
Yes, and we will see how we're gonna. This is something that we address. So the other thing, switching context a little bit, and then we're gonna go back to this. Now, putting something in an isolated page is not enough to actually. Well, It is great because it provides the integrity to the contents of that thing that I put there. Again, be it page tables or creds or whatever. But let's say we have a scenario that someone was saying before, I have a task struct, it has a ton of pointers basically to stuff like that. Maybe I cannot really, so you have, let's say the credentials here. Maybe I cannot go here and change the credentials themselves. But what I can do as an attacker is go and corrupt the pointer to the credentials. Make it point somewhere else, maybe another piece of credentials which are more privileged, or I can inject my own credentials, put whatever values I want there and make the pointer point there. So isolating data is nice as a primitive, but it's not enough. So we also need to kind of have some form of integrity for pointers to data which are isolated. This means pointers to page tables, pointers to creds, or whatever else you're going to isolate. Okay. Now for that we have a scheme which we call it context-bound pointer integrity. And this is a way to authenticate pointers by using a small HMAC. Okay. The way we do it today in ARM, you have pointer authentication. That's exactly the same thing. Back in the day, we tried to actually kind of perform the same thing in an architecture that doesn't have natural support, support directly for it. So the way we do it is that for every page, if you have isolated here all the credentials, then in that page, we can also put a key, in that domain, we can also put a key which is only available when that domain is active. And we can take that key and use it in order to perform an HMAC on pointers that point to data into that domain. And then every time we're going to be doing a domain switch, we're going to be verifying the integrity of that pointer. If that pointer, so we instrument the code, if you are dereferencing a data structure belonging, let's say, to that domain, you have to do a switch, take the key, compute the HMAC, and then access the data.
Where's the HMAC stored?
In the pointer itself.
That's part of the pointer.
Yes.
So you're making the pointers longer.
No, we actually use unused bits. So 48 to 30 to 63, it's there, and then we mask it and take it out.
That's very short. Okay.
Yeah, we use SIPMAC and we shorten it as well for this particular.
It's not accurate.
Yes. Future research.
Okay.
So that's the idea behind this. Now, as we were saying before, you also have a lot of situations that we need to protect when certain things happen in the system. Think about context switching. So I'm switching from one kernel thread to another. At this point, I had active domain 3, and then I go somewhere else that I need to run with restricted, and then I need to come back and activate 3 again. And if I can tamper basically with the arguments to VM-func, maybe I can run, enter in a domain, enter a piece of code with the wrong domain. Yeah. So how do we do that? Every time we basically spill state with respect to what was the actual protection domain, we use the same technique that we had before in order to bound that thing, basically, mark it and make sure that this thing has been bound. And where do we store that? You can store it in task struct. Have fields for the kernel active domain and the kernel, the user active domain. So you do integrity protection there every time you do context switch and interrupt handling. Now, this particular prototype provided support for specifically page tables and credentials. That's why I keep mentioning those things. The way we do that is that basically we take the body allocator and we make it XMP aware. The body allocator is one piece of one part of the allocators that Linux is using in order to dynamically get data. And this is what is used in order to get pages to store page tables. All right. So by making the body allocator XMP aware, you can say, okay, give me 10 pages. And by the way, put them in domain 1. Okay. Credentials come from a SLAB allocator. You can do the same thing. You can go there. We modified it. We have produced our own XMP aware SLAB allocator. You can say, allocate objects from the general allocator or allocate objects that belong into this particular domain. Okay. And for that, we have basically made the cred jar, which is a cache only for creds to allocate things in domain 2. Let's say domain 1 is page tables. Then all these things become isolated in separate domains. Pointers to those things are integrity protected using the pointer integrity protection scheme I said before. Every time you have an update, every time you take CR3 and you update it with the new PGET pointer, you also need to make sure that this is valid, it's not have been tampered with, and we use again the same integrity protection mechanism. So let's jump to performance. Okay, how expensive that thing is. Well, it depends on. It's not that expensive, to be honest. Like, but it depends on, like, first of all, how many data structures you're protecting, how many different kinds of data structures you're protecting at the same time, and what exactly these benchmarks are stressing. Okay, so we used the Phoronix test suite. It has a bunch of stress tests and real-world applications. Like Apache is a web server. Kernel build, it builds the kernel. Kernel extract, it extracts the kernel. This thing is basically a humongous multi kind of process benchmark.
These are all times,
So it's relative. It's
percent time, right?
right. So it's normalized to the execution time of the benchmark for vanilla. So on average, well, not on average, tops, let's say we observe 12% overhead in the kernel build. It also, kind of depends on what kind of, protection we're providing. In that case, the majority of the overhead comes from the page tables. Kernel build, think of it as make, like a parallel make. It's gonna build it's gonna create a ton of processes, and therefore page table kind of isolation becomes where is the element where the majority of the overhead comes from. In other cases, like Apache, for instance, here you see that it's the CRED protection that contributes more to the overhead, because if you think about it, every time it needs to access something in the file system, there's going to be, or perform like a network operation or things like that, there's going to be an access to the CRED structure for that particular process. So yeah, that's XMP. Let's move on quickly to SafeSLAB. SafeSLAB is a more recent system that we built in order to protect the kernel heap. Okay? It's basically it's a system that we say provides protection against address reuse attacks. If you remember the kind of diagram that I used in the beginning about like this difference between temporal and spatial memory errors. In the temporal scenario, if just to remind you how it works, the attack, you have the attacker basically allocating something. You have a pointer here. You deallocate this pointer becomes a Dublin pointer, then another allocation happens, an object lands here, and through that pointer, you're able to either corrupt it or reference it. Okay, that's the model here. Now, one way to basically solve this problem is which is not something that we have, invented by any means, is to kind of try to prevent address reuse. Okay? Because if I had allocated something, then deallocated, but the next allocation was, like in a different place, you would never have this aliasing problem that we had before. So this is basically a hardware-assisted kind of approach to try to delay address reuse as much as possible. And whenever we actually going to do, as you will see in a sec, the way it works is that whenever we're going to truly reuse things, we're going to do it safely. So basically, it uses address aliasing in a, I'm going to say clever way, you will see, that allows physical address reuse. So we don't really waste too much physical memory, but not virtual address reuse. So basically, we're trading virtual memory for physical. There is also a memory quarantine component. We're going to see how it works that allows for physical memory reclamation in a safe way. And in order to do this fast, we also use Intel MPK, which is a memory tagging scheme. So the thing that this thing protects against is stuff such as use after free, double free, invalid free kinds of vulnerabilities, or sorts of vulnerabilities that allow in this kind of address reuse problem. That's a thing you need to have in mind. Now, the way, like the very high level idea of how SafeSLAB works is the following. You have, as we discussed a little bit before, the heap allocator is built on top of FISMAP, which is the region that takes the whole RAM and pre-maps it into that location. Okay? So here's what we're going to do. We're going to take the RAM and we're going to map it 15 times, create 15 aliases of FISMAP. Okay? So we have one FISMAP here, another one here, another one there, yada, yada, yada. Okay? All these things are aliases of the same physical memory. Okay? Now, every time one of them, every given time, only one of them is active. So how do we disable the rest? Using memory tagging. So we tag those pages here with a key which is not active. For those who are not familiar with Intel APK, basically you can allocate you have 4 bits that you can tag every memory page, and then you can say, make all the pages in, I don't know, domain 1, you can make them non-accessible, or readable only, or read and write, whatever. So using Intel MPK, basically, we can disable all the other alternative aliases and have, at any given point in time, only one action. Okay? So we call this the temporal aliasing domain, or TAD. Okay? Now, once we start, basically, once the kernel starts executing, you're going to keep allocating objects. Okay? You allocate something, you do whatever you have to do with it, and then you free it. When you give it back to the kernel, the kernel is not going to reuse that at all. So if you say, again, alloc, it will never give you a block that was deallocated. And so, again, think of it as you allocate, let's say, 64 bytes, you use them, you gave them back. If you say it's free, but if you say alloc it again, it will never give you the same block. Okay? So it will keep going up in terms of, kind of consuming memory within the TAD. At some point, the stuff here which are kind of free, they're going to make pages. Okay? When the whole page is free, then despite the fact that it's not used, that allocator here, SLAB allocator, the SafeSLAB allocator, is going to give it to a component which we call it the quarantine component. So that component is keeping track of pages which are released from the tab but still not used. And we're going to keep doing the same thing. At some point, we're going to run out of space. Okay? Because we're not reusing. Okay, so if I have an application that basically causes the kernel to do alloc all the time, I'm going to waste the whole thing here. At the same time, whatever is freed, I have reclaimed it, but I haven't used it yet. So when the whole TAD is done, we're going to do a TAD switch. So we're going to enable, let's say we were in TAD 0, we're going to enable TAD 1 and disable TAD 0. So these addresses here, virtual addresses, still map to the free pages in the physical RAM, but in terms of virtual addresses, these are different virtual addresses. So if I actually give back one of the physical pages that was reclaimed before, it's going to be with a different virtual address. So in the virtual domain, I never end up with 2 virtual addresses in the same location. Okay, and the same thing happens again. Okay, so we move on. TAD 1, TAD 2, TAD 3. Of course, you may ask, okay, at some point you will go up to TAD 15. What are you going to do? Okay, you run out of virtual address space, basically. So at this point, we have to go back in TAD 0. But if we go back to TAD 0, we may still have some dangling pointers with virtual addresses in this part of the address space here that can be exploited. How do we solve that problem? This is where a pointer scanner component is going to kick in. This is garbage collection, basically. Okay, this is expensive. That's why, as you saw, like we try to delay doing this as much as possible. We have the TAD thing. We kind of reclaim things. We quarantine them. Then we change the TAD to trade more virtual address spaces before we do the reclamation here. And we try to delay that as much as possible. How many times we can delay it? Based on, it depends on how many keys we have. MPK allows us for 16 domains, 15 TADs because key 0 is special. Once we go here, the pointer scanner is going to kick in, and it's basically literally going to scan all the heap to find dangling pointers for the references, for the addresses here in TAD 0. This is expensive. So that's why we want to avoid having it as much as possible. But it will happen if we run out of virtual address space, basically. So how expensive it is? It depends, again, on the workload, right? So what we have here is LFS in the top. This is for Onyx Test Suite. These are kind of real workloads similar to the one that we saw before for XMP. Now, in most cases, both in micro and macro benchmarks, the overhead doesn't go over, the runtime overhead doesn't go over 5%. Because literally that is going to come from the fact that you're not using your caches in the most efficient way that the default allocator is using. There are certain things, though, that can go up to 50% overhead, and this is basically where the scanner kicks in. Okay? So these applications, for the setting we had here, which is, I think, 64 gigs, one more thing. The more physical RAM you have, the more you can delay the scan, basically. Right. So
the longer the scan's going to take.
Sure.
Yes. It's always a trade-off. Like, I'm pulling.
The amortized cost will be the same.
So, but there's also a trade-off there, right? So if your workload allows you to do that, or basically fits there, you're good. So yeah, so that can go up depending on, like how many times, if you're running something that is basically gonna saturate the paths. In these cases, like this only happened, so even in real world settings, it didn't happen that often. It happened only on hackbench, which is basically a stress test for the kids, so it makes sense. Now, if we see here, of course, the actual memory that is consumed. So this is the maximum resident set size for various macro benchmarks, like real world applications. I mean, in most cases, it's a couple of megs, but you do have situations like SQLite, for instance, that the memory, the maximum resident set size went up by 60 times. That's fine though, because 62x. 62x, of course, it was like 135. So that under normal circumstances, the RSS was basically 2x. But still, it's a big thing.
It's no longer light.
Yeah, the thing though is that, like if you have 64 gigs of RAM, the idea here is that you can, if the workload allows it, like, we can actually keep doing this until we blow up. And, like the actual, here there was no contention, so it didn't affect it.
This is one SQL. Typically, you might have several.
Sure. Basically, the more stress you have in the system, it's like, you're going to have this situation showing up more frequently. Because these 64 gigs are going to become effectively less. All right, so let's move on to how much more time do I have?
5-ish minutes.
Okay, very quickly, let's talk about EPF and then maybe wrap it up. So basically, EPF is a project that has also like a defensive and an offensive element to it. So with EPF, what we try to do is to basically exploit and also protect the BPF subsystem. Okay? So for those who are not familiar with what BPF is think of it as a universal in-kernel virtual machine. It allows you to kind of extend the functionality of the kernel by pushing small programs written in a language and an architecture which is called BPF. That can do things such as system call filtering, packet filtering, network routing, yada, yada, yada. Okay. BPF basically comes into two forms, the classic BPF or CBPF, or the extended version of it, which we call it the eBPF. The instructions for both architectures or VMs are the same. They're 8 bytes each. The difference is how the ISO looks like. The original one only has 2 registers and 16 kind of memory locations, all of them 32 bits. The new one is more like a RISC-like modern architecture with 10 registers, 64 bits. It also has the ability to invoke native code. So the BPF program can invoke certain kernel functions and has access to something which is called BPF maps that allows persistent storage. So a program runs, it can store something, if it runs again, it can get it from there. Think of things such as key value stores, arrays, and so on and so forth. Now, the instruction set allows for things such as ALU, memory load store, all sorts of usual things. It is interpreted and JIT compiled. So you can have that thing only interpreted, both of them, or you can also JIT compile it in the underlying architecture. In the beginning, they were maintaining all, like 4 different versions, like, an interpreter for CBPF, an interpreter for eBPF, and also the JIT engines. Now what they do is that they take the CBPF, translate it internally into eBPF, and then have only one interpreter and jitter as a runtime. Now, the important bit here is safety. Okay, so if you have a program that you're pushing, like an arbitrary program that you're pushing in the kernel, you want to make sure that certain things hold true. One very important is termination. Okay, you shouldn't attach a program somewhere, let's say, in the path that receives packets, and then that thing never terminates because then it's game over. Right? So the other thing is pointer access safety. If that thing has pointer accesses, you need the verifier, which is a huge component in eBPF, needs to make sure that all these things are within bounds. They do value range analysis to make sure, like, how exactly that thing is going to be accessing a network packet, let's say, if that's the scope of that program, and so on and so forth. So what we try to do here is to see if we can actually go around the safety guarantees that the verifier provides. And what we do here is basically something very simple. We still assume that we have a memory corruption vulnerability. And what the attacker tries to do is what we are wondering is that, let's say we still have a memory corruption vulnerability. Can we abuse this thing to do something better than just data-only attacks that we can already do with our memory corruption vulnerability? And the way to do that is to force basically the BPF interpreter or the BPF engine execute a program that was not verified. How are we going to do that? We're gonna do that by borrowing this whole concept of reusing code. So think about a legit program that was verified. It's the one in the top. The bytecodes for the instructions are the ones shown here, and basically all these things are instructions that they just load a different value in register R7. If you have this as a program and you pass it to the verifier is saying, okay, first one is loading this value to R7, second one is loading this value to R7, there's nothing wrong there, no pointer arithmetic, everything is valid, do as you please. Now, if at runtime though, we can go and corrupt either the pointer that points to the beginning of the program or something else that allows the execution of that program from an offset, then as you would imagine, a different sequence of bytes is going to be interpreted and then ultimately JITted if the JIT engine is there. That will basically result into a whole different set of instructions showing up. These instructions were never verified by the verifier. Okay? And this is basically something that allows us to do things such as, let's say, dereferencing memory from a location that the verifier didn't. So this is, you can think of it as, like the embedding an unsafe BPF program inside a safe one. We call that EPF1 or BPF reuse. In the interest of time, let's skip this. Or not, maybe I should go back. So how effective that is, what we did is that we took a bunch of actual real-world exploits spanning various vulnerabilities like heap overflows, arbitrary writes, and stuff like that. These were all prevented by reto-user or code reuse mechanisms that are available these days. And we can actually go there and kind of update the exploit to use the EPF1 technique that I showed you before, going around the deployed mitigations and showing how you can actually weaponize a little bit this universal VM. Very quickly, I'm just going to mention 3 defenses. So how do we solve these things? We have, if you're interested in the paper, 3 schemes to actually defend it. The important one is NX and CFI. So what we do is that we create a region in the kernel, a sub-address space only for BPF programs. So if we do that, like if you have a pointer and you somehow redirect it into arbitrary data in the kernel space, the interpreter and the jitter later on are going to actually prevent you from fetching an instruction from a region that doesn't fall inside here. So this is a trusted part of the address space that you can only have BPF code there, BPF programs there. Nothing else gets allocated here, so we don't mix with other kernel data, and that thing is immutable. So the moment you allocate a program here, it becomes redundant.
Change the offset.
No, this is only when you actually want to inject, let's say, a completely unverified program and try to execute it. How we do that? Kind of offset, solve the offset attack with something like, we draw again an analogy from CFI. So basically what we do here is that we make sure that first of all, we do alignment tricks. So we align the programs in certain addresses, and then we have the interpreter make sure that we're only going to start the interpretation from the beginning every time. So both checks are in the interpreter. If you JIT it, then it's the legit code that was JIT. So that's the high-level idea behind it. Now, how expensive that thing is, it's not expensive at all. So what we have here is system call filtering. This is Nginx and Redis. This is without system call filtering at all. This is with system call filtering, but the BPF engine is not hardened with our scheme. And then this is what we do. This is what we have when we employ our defenses. So basically, the overhead is 100% in system call filtering. 1 to 3% if we're talking about packet filtering. So let me stop here because we're going to run out of time. Thank you very much for the attention, and yeah, happy to take questions.
Time for maybe one very quick question. If not, that's okay too. Right?
Yeah,
EPF has been integrated into current CBPF?
No. So the thing is that there are certain features that people are considering. Actually, they invited us to this Linux Plumbers conference that is going on, and we presented that. Now, What are they gonna eventually get out of this and integrate it there? I have no idea. One concept though that I think it kind of draw their attention at was the concept of having a separate sub-address space for BPF programs. So we may see that at least, because right now everything is mixed. So they basically allocate the BPF programs from the heap. So you may have a BPF program followed by, I don't know, an inode or whatever.
I mean, if it's not like that hard to implement in the kernel, I don't see any point of not doing that.
Yeah.
It seems very.
Because it's already such a mess anyway, so why does it have it? That's the argument.
So you're
Actually,
you're
there's-
volunteering to maintain it then?
There is a configuration option to actually strip the interpreter completely. Yeah. So someone, has a configuration option that says you can kind of completely strip off the interpreter. Anyway, I'm not sure where this is gonna, result.
All right, let's thank Vasileios one more time.